So what we're focusing on in the next few sections is, given a series, an infinite series, like the sum from n equals 1 to infinity, 1 to infinity of a sub n, whatever a sub n is, the question is, does it converge, does it diverge? We often don't care what it converges to, we just want to know if it converges. And we're going to present a series of tests to help us determine whether or not it converges. And what test you use really depends on what kind of series you're given. So in this section, we're talking about the integral test and p-series. The goal is to apply the integral test and p-series test to determine if a given series converges. So here's the theorem. It's called the integral test. And all the tests in the next several sections are designed to show whether or not a particular series converges or diverges. Interestingly, though, many of the tests do not help us determine what the series converges to. If you know it converges, but you don't know what it converges to, then at least numerically you can get something close by using your calculator and adding the first 1,000 terms if you need to. Okay, the integral test. Let's let y equal f of x be a function. If f is, all right, it has to be positive, continuous, and decreasing. PCD. Hopefully that doesn't stand for anything bad. It's always dangerous coming up with acronyms. PCD, positive, continuous, decreasing. You have to know this. So f has to be greater than 0. That means f is positive, right? F has to be continuous. And f has to be decreasing. So if you draw the graph of it, it goes down as you look at it from left to right. Positive, continuous, decreasing. And that's for x is greater than or equal to 1. We don't really care what's happening elsewhere. And, okay, f of x, where does that come from? That's the function that corresponds with a sub n. If you just restrict the domain of f to the natural numbers, then you get a sub n. Okay? Then it turns out that both the series, the sum from n equals 1 to infinity of a sub n, and the integral from 1 to infinity of f of x dx, they either both converge, they do the same thing. They either both converge or both diverge. So that's what I'm filling in here. They either both converge or both diverge. And that's the integral test. So the idea is we have more tools for determining whether or not the improper integral from 1 to infinity of f of x dx converges or diverges. So if we can figure out if the conditions are met and we can figure out whether or not that integral converges or diverges, then we know about the behavior of the related series. So that's where we're going with this. Now, the first question on your mind should be, well, why? Why does the fate of one determine the other? They're like entangled electrons or something. I don't know. Well, this is a good time to remind you of what the heck an integral really is, right? Let me draw a picture for you. So here's x, the x-axis, the y-axis. Let's just draw a nice, lazy, continuous function f. Now, this function actually doesn't satisfy the conditions of the integral test, but it doesn't matter. I'm just trying to remind you what an integral really is, the definition of an integral. So let's say we're looking at the area underneath f from a to b. And it really will be an area because f is bigger than 0, but okay, that doesn't matter. It doesn't have to be. To define the integral, f does not have to lie above the x-axis. It's just convenient to make it do that. So let's say this endpoint is a and this endpoint is b. Remember what we do to find the area and then more generally define the integral later on between the curve f in red and the x-axis is we split up the interval from a to b into n subintervals. Does that sound familiar? I can't draw n subintervals, so I'll just draw several of them. That's probably a little too wide. So I'll draw a few of them and then I'll do dot, dot, dot as if there's a whole bunch of them. And then corresponding to each subinterval, there is a
Well, we think about rectangles when we first get introduced to the definition of the integral, right? And finding the area between the curve and the integral. So now there's different ways to pick the height of the rectangle, but the function is going to determine the height depending on what value you pick in your subinterval. But I'll just draw it. I'll use right-hand endpoints for this drawing. So there. But you don't have to. You could pick any point inside the relevant subinterval and then take f of that point to get the height of your rectangle. Then there's a whole bunch more. Okay, so that sort of picture look familiar to you? Okay, so then what is the integral? Well, the integral from a to b of f of x dx, which will represent area if f is non-negative, right? So in this case, it represents area. It doesn't have to, though, if f is negative. So the integral is defined as the limit as the number of subintervals goes to infinity, right? That's the same as saying the number of rectangles goes to infinity of the sum from n equals, well, let's use I equals 1 to n. Otherwise, it won't make any sense at all. Of, let's say, f of c sub I. So c sub I is some x value inside the ith subinterval times delta x. Okay. Looks complicated, but all we're saying is this. If this is the height, that's the height of the ith rectangle. And this is the width of the ith rectangle. They don't all have to be the same, but oftentimes we take delta x to be the same for each rectangle to make things simple. And then what the summation says is if you add those essentially areas, right? You're multiplying height times width of each rectangle, so you're getting areas. If you add all those together, you're going to come up with hopefully a decent approximation of the area underneath the curve. But if you take the number of subintervals to infinity, assuming that limit exists, you get exactly the area underneath the curve, right? If f is non-negative. And so that was the idea you were introduced to kind of towards the end of Calc 1. Does that seem familiar to you? So notice what we have after the limit symbolism, though. We have a series, don't we? So although an integral is not a sum, right? It's a limit of a sum. There is a connection there. And we're going to use that connection to help establish the integral test. Remember now what the integral test, it says, as goes this integral, if it converges, so goes this sum. If this integral diverges, so does this sum. Okay, so let's see why. So I've drawn two pictures for you, and notice the f in these pictures do satisfy that f is positive, continuous, and decreasing.
So suppose I plug in right-hand values to get the heights here. Then this height here is the A2. This height here of this rectangle is A3. This height here is A4, and so forth. And then it's pretty clear that the sum, n equals 2 to infinity, I have to start at 2 here, n equals 2 to infinity of a sub n would be less than the area under the curve, wouldn't it? Because this sum would be represented by the area, the sum of the areas of these rectangles. And of course, you keep going. I just can't draw forever. So when you start at n equals 2, it's pretty clear that the sum from n equals 2 to infinity of a sub n is less than the area of the curve, which is equal to the integral from 1 to infinity f of x dx. Would you buy that statement? So, yes?
Would it be 2 to infinity since we started there?
No.
Okay.
No, I wanted to talk about the entire area under the curve, which starts at 1 in this case. But just adding in one term, a1, would make that series complete, wouldn't it? So that one term is not going to determine the divergence or convergence of that series. So if this guy converges to a finite number, then what's going to be the conclusion about this guy? It converges. Right? Because it's less. Term by term, it's less, so it's got to converge as well. It's a type of comparison, isn't it? Now, adding in A1 makes it the complete series, and so A1 is a finite term. So if the series from n equals 2 to infinity of A sub n converges, certainly then you can conclude starting at 1, going to infinity, converges also. So what did I just make you believe? If this integral converges, then this related series converges. And realize they're not the same thing, right? An integral and a series are not the same thing. But we can get some information from that integral. If that integral converges, then certainly that series converges. Did I make you believe it for the case of convergence? Okay. So that's what I was after there. Now, we can create these rectangles differently. If we plug in left endpoints, then we get the height of this rectangle and the area of this rectangle, for that matter, since the width is 1 on each one, is A1, because I plugged in the left-handmost value here. Likewise, the height of this rectangle and the area is A2, and so on and so forth. So that if you wanted to think of the series n equals 1 to infinity, A sub n, in terms of area, you could just add these rectangles together. But you can see from the picture, geometrically, that this sum, this infinite series, has to be greater than the area underneath F. So what does that tell us if the integral diverges? Well, if it diverges, it's going to diverge to infinity. So if this area underneath the curve, which is represented by the integral from 1 to infinity of f of x dx, if that diverges, then what's the conclusion going to be about a series that has to be bigger than it? Then this divergence is going to, the divergence of the integral is going to make the series diverge. Does that seem reasonable to you? Okay, well that's it. That's the argument. That's pretty darn convincing.